Okay. So when we've been talking about open channel flows so far, you'll recall that we made this division into three different groups. The first were uniform flows, the second were gradually varying flows, and the third were rapidly varying flows. Uniform flows are where the upstream and downstream water levels or water depths are identical, and it's a very simple calculation then to be able to calculate flow rates based on that. But of course, if you're given a channel and you're going to put water through it, you have to figure out whether, of course, it will be uniform flow or not. And so the question is how you have to do that. And so one of the ways to do that is to be able to look at what the conditions are where you'll get these other kinds of flows. Either gradually varying flows, which is what we began talking about last time, and which we'll recap, and then rapidly varying flows, of which an example of those is the hydraulic jump or waves on rivers, which are really a little bit like waves in the ocean, but you just have a different frame of reference. And so you can imagine that in some cases, let's just see if anyone has been able to get on yet. Still loading, so I'm not sure if this is the right one. You can imagine, for instance, that if you look at what's called a hydraulic jump, which is a rapidly varying flow, by the way, which we haven't talked about yet, then we laid the ground rules for it last time, and the ground rules are that because the surface of the water is kind of a free condition, it can choose to either be shallow, as you have on the left-hand side, and flowing very quickly, or deep, as you have it on the right-hand side. I guess I can't write on it with this, and flowing much more slowly because it satisfies continuity. The volumetric flow rate has to be the same as you go across any section as you go from left to right. Then because it can self-organize itself in either of those two modes, we have to understand exactly what the conditions are that allow us to do that. And so that's what we'll finish off today, is talking about this concept of the energy equations. And so it turns out that out of the three classifications we have, obviously this isn't a uniform flow because the upstream depth and the downstream depth are not the same. It possibly could be a gradually varying flow, but it isn't, as we'll see later on. And it's actually the most extreme of the cases, which is this rapidly varying flow. And so what we've done is we've actually taken this one-dimensional Bernoulli's equation. So you could write Bernoulli with the energy loss terms. You'll recall that the energy equation is in one-dimensional form is really the Bernoulli equation with a pump term in it on the left-hand side and a head loss term on the right-hand side, typically, as we write it. We don't care about pumping in these, so we just have a head loss term. So the energy equation is just Bernoulli. And we can write it in a slightly different way to be able to equate the energy upstream at point 1 and the energy downstream at point 2. And we can use that to be able to understand exactly what's going on. So let's recap just what we did last time. All right. So what we had dealt with last time was this so-called gradually varying flows. And so I can't write on this very well, but I'll take you back to maybe a summary slide that says a couple of important summary slides. So don't get whiplash on this, but this is a key one, right? One key observation was that we could have different flow regimes. And this is slightly backwards from the way you had it on the screen. You had this hydraulic jump, which was shallow and then deep downstream, but it's the same idea. And that is that you can have the same volumetric flow rates going in each of these sections, but if you do that in this one, then you have to be flowing much faster than you do in this second one. And so the way we rationalized that was that in writing the energy equation, we could take Bernoulli's equation just as we had it before, which is just this term here, as exactly you've seen it before. Has a head loss term to account for friction losses. The pump input term is not there because it's irrelevant for these open channel flows. And all we did was with this energy equation was that we made a substitution for the fact that the pressure at the bottom of the flow was equal to the height of the flow. So this term was just equal to the height of the flow. And this term here we could define not in terms of the upstream velocity, but a more convenient term, which was the flow rate per unit width of the channel. And if we did that, we ended up with this exact equation here. We could write it in a couple of ways, but this is probably the easier way for you to think about it. And that is that if you put the pressure head and velocity head terms in this energy term, which is this. So this is the pressure head term, and this is the kinetic energy head or inertial term in here. And this is just the elevation. And if you put again the downstream location, you have the pressure head and velocity head terms in here and the elevation term here. Then we merely write this energy term. It's convenient because it includes the flow rate per unit width of the channel and also the depth of the flow. And so what we could do is we could look at this energy, specific energy term, and we could realize that if we look at it not as a quadratic and a y to the minus 2 term and a y term, we could actually write it as a cubic, where you have a cubic equation term, a quadratic term, and a constant, and then it should look like this if you plot the depth of flow versus the energy that's there. And because the cubic term has 3 roots, and the important thing to know about this expression are that, as you can imagine, as the depth gets very deep, this very subcritical flow, then this term here, if y gets to be very large, then this y gets to be very small, and so in the limit, the energy is equal to the depth, which is this one-to-one line here, so that has to be one of the bounding lines. And there's also a minimum energy that we can define, which is this point here. And this point is given, you can do the math, it comes a little bit after this, and the math is that the minimum energy, let's see if I can do this, oh, it's very skillful, look at this. This is min. Sorry about this. And it's equal to, it's quite an important expression, that's why I'm belaboring the fact that is to 3 halves times y critical. 3 over 2 times yc. It's a c. Right? So this point here, which is also where, by the way, the Froude number or Froude number is equal to 1. So draw yourself a nose diagram, because these are the important ordinates, if you like, on it. So the fact is that we can define these particular ordinates. So if you have, for instance, a particular energy of flow, so you can take the upstream and the downstream energies, they have to be, let's say they're the same for conservation of energy, if we have no viscous losses in the system. Then if they're the same energies, then you would know that the upstream and the downstream levels would actually be equal to these magnitudes that you have here. That's really all we're saying. And so these are the 2 potential elevations of water. This is y, I guess, deep, not downstream, but deep. And this is y shallow, if you like. And so they correspond to these 2 little positions here. So this would be, this one here would be this. And this one here, a deeper flow but more slow, would be the top one. So that's all it is. So it's nothing more than that. So we've taken the energy equation. We've chosen to write it in terms of this parameter here, specific energy, instead of the velocity squared term and the pressure term. And if we do that, we can end up with this specific energy versus depth diagram. And it's actually quite straightforward in terms of how we might want to use it. We know the ordinates of this nose where the minimum energy is present. And we also know the ordinates if we have a given amount of energy upstream and downstream, what the depths would be at those 2 locations. They could be upstream and downstream, or they could be downstream and upstream. But that's the basic idea. And so we did some math to be able to do that. And I guess the other thing that we would also note is that the Froude number for this would be greater than 1. This would be, sorry, less than 1. The top one would be fluid less than 1. And I won't write it out, but that's subcritical. So that's this one, the deep flow. And this one would be more than 1. So anything above this minimum energy along this trajectory would be less than 1. Everything below that would be bigger than 1. And by definition, this would be subcritical and this would be supercritical, just by our way of dealing with it. Nothing to do with supercritical CO2 or anything like that, but just a statement of the state of the flow. And so the practical way of dealing with this is actually relatively straightforward. And this is the basic idea here. And so what you could do is you could take a situation that has a sluice gate on it that cuts off flow and impounds water partly behind it, but allows the flow to occur underneath it. If we knew or could calculate, for instance, what the flow rate was along this bed, we know that, for instance, Q1, the flow rate coming into this upstream portion, has to be exactly the same flow rate going out of the bottom, just from continuity if it's not piling up somewhere. And so what we could do is we could take a magnitude of Q, and if we know what this upstream, we just take a magnitude of Q, and for every possible depth we could calculate one of these curves, right? You could assume a value of y is equal to 0, and at 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, etc. And you'd get one particular curve. And the curve you'd get would be this middle curve, which I'll try and draw on top of in this particular diagram, because this is the curve for where the flow rate Q is equal to this magnitude of Q. And so physically what that means is that if we calculate what the energy was for the location that's upstream, by definition, the energy would actually be on this line that comes down through this point. So we know that the depth of flow upstream is here. We know it would intersect this y equals, the energy line, which is the red line underneath this, not the y equals E line. And that would be the energy that's upstream. And by definition, if we don't have any losses in our system for viscous losses, in other words, this drop in the energy grade line was 0. The slope of the bed is also 0. This is just the other way to write this, by the way. So you see this, I noticed, right? You can write it in this form with the elevations of the bed, or you can write it in this form with the slope of the bed. They're both the same as each other. But what we're doing here is it would allow us to say something about the flows that we have upstream. So upstream is what? Less than the critical Froude number, so this is subcritical. And then downstream, it's supercritical for it's below. So what could we do with that? Well, there are a couple of things that we can do. So these are the things that we would think about doing. So what we could do is we could raise the upstream level but keep the flow rate constant. And if we want to keep the flow rate constant, if the upstream level goes higher, you'd expect that it would flow faster because of the equation basically of a free jet. So you can stop it flowing faster by shutting the bottom of the gate down somewhat so you stay on the same curve. So what we're going to do is we're going to raise the level of the upstream to some higher value. And if we do that, obviously we have to have a gate here. And we're going to move this down slightly so it's no longer the same magnitude, same height. So it's moved down. And so in doing that, we want the same flow rate to be going through as was previously going through. The reason for doing that is if that's the case, then we'd still be on this same line that is the same energy depth curve, specific energy depth curve that we had before, which is for this Q equals Q0. So this is equal to Q0 still. Can't write it very well, but it's there. And so if we shift onto this lower diagram, now this outer curve here is this former one that we just highlighted, which is the red one on the one above. This is just showing that if you have a smaller flow rate going through, you'd end up with a different specific energy curve. If you have a larger flow rate going through, you'd have a different specific energy curve as well. But so if the same flow is going through, then before our gate was this tall, and it went through this point 1, and this was our gate. And let's see if I can draw it. You'd probably like me like this because this stops me from actually doing anything very quickly. And so from our point before, this was our point 1, and the point that we had here on this same curve was this downstream point, which was here. So this was the original depth of our gate. What we've done now, I guess I should have finished the gate at this level. So that was our original water level that we had. So now what we've done is we've put the gate higher. We've lowered this slightly to be able to keep the flow rate the same. And as a result, the water level here has risen. Right? So this is the first case, just the same as the first case here. So now what we've done is we've raised the water level. So the same now is this curve that goes across here. So our new point on this curve is here. And so we know that the upstream energy and the downstream energy are the same because we're assuming that there are no two things. There's no losses in the system due to friction, and the bottom of the bed, this lower level here, is horizontal, both upstream and downstream, so there's no gradation on there. And so now as we've lowered this gate here, as we come across, instead of being exactly on the same point, we'll be at point 2 prime. And so we're still on the same curve as we had before. It's the one that we had here. But now we've physically moved ourselves over. And so now, if we know what the upstream level is and we know what the flow rate is, de facto we can calculate what the downstream flow rate is as a function of that. And that's basically the desire of this. So the other thing we could do is we could also try and, instead of messing around with the gate, we could start off with the gate exactly where it was before, and we could just put the height of water upstream higher. And if we did that, we'd expect that the flow rate out of the bottom would be larger. Right? So we start off with the gate as we had in the first place up here. And now, instead of having the water level set here, we increase the upstream flow rate so the water level goes up to some higher magnitude. So now the flow rate is no longer Q0, but it's Q0 plus some amount. It's larger. And so if that's the case, then we'd expect to be on a different specific energy diagram. And so that would be given just by taking, for instance, this larger value of flow rate that we now know, taking the upstream and going through a whole bunch of different depths for the flow, which would be from 0 up to higher than the gate, the top of the gate. And if we did that, we'd get a second specific energy depth curve, which would be this one here, for a larger flow rate. And so that's just shown on here as this second curve here. If I can draw it, this is Q is now greater than Q0. If you believe that I'm writing this, Q0. And so now, if we know that the upstream level is here, we can do the same thing. This is the upstream level. We go across to where we hit the specific energy curve here. We know that this is the energy within the system, and as a result of that, we can figure out what the downstream depth would be also. And so it just gives us a way of being able to figure out what the upstream magnitudes would be. And so really, by having some kind of structure in here, we're forcing it to be able to organize in some way subcritical upstream and supercritical downstream, and it's caused by the fact that we've put this physical gate in the system. And that's really all it is. So that's the technique, if you like. So if you don't have a uniform flow, when you can use the Manning or Chésy formulas, then to be able to figure out exactly what the flow configuration is, then we need to use some concept like this. So it's important to be able to rationalize that. And so this is kind of engendered, if you like, in the surfing West Virginia videos we looked at, because you could imagine doing this not necessarily with a gate that comes across your flow section and causes upstream to be subcritical and downstream to be supercritical, but you could imagine it occurring in a variety of different ways. So here's an example that kind of illustrates that point. So it's in English units, but let's not worry about that. And so Water's flowing happily along at 2.3 feet deep. It's flowing at some given volumetric flow rate per foot width of your channel. And it's happy going down there, would just continue going down at that rate so long as nothing happened. And now what we're going to do is, instead of allowing it to keep on, so it's come from the left-hand side, and it's been this depth all the way as far as we can see upstream, which is 2.3 feet. That's a 2, in case you couldn't tell. That's a 3, in case you couldn't tell. And it's happy trucking on down at that same level, and it would just continue along if the bed dimensions didn't change. We presume that if you look upstream at this point 1, that we could calculate what the energy was at this location. And we can certainly assume that this is maybe the datum here, datum, which is equal to the elevation, which is we're going to call equal to 0. And so we have two important concepts. One is that we have this energy equation, bless you, which is just Bernoulli written between upstream on the left-hand side, downstream on the right-hand side, and we're going to assume that the loss in the system is 0, because we can. And secondly, we can draw this depth versus energy diagram, because we can write out, I don't want to write it out, we can write out this equation, and we know everything we need to know. So we know what the flow rate Q is. We know the upstream flow rate is 2.3, but we could also make the depth equal to 0 through to 2.3 in some increments, and we could draw one of these diagrams for that. And so if we do that and plot this value of E as a function of depth, then we get this one curve here. This is the curve from doing that. So we plonk in 5.75 square feet per second, and we do depths of 0 through to 3.2 in this particular case. That's the top curve, and we end up with this curve for that particular flow rate. And so we know that as we look upstream, the depth is 2.3 feet, and so if we take 2.3 feet and go across here, then this has to be the energy that we have at point E1 as we come down to here. So the energy at point E1 has to be 2.4. We know that. So energy, what are the units of energy? Well, we know that we have to add apples to apples. So this is a depth. So energy, specific energy is a length. And so the other axis in this, and I can probably draw it large, make it larger. So the axis, the units of this axis for energy are also length, the same length as this. So we know that the downstream energy at any point here would be 1. But as we go past this point, we're going to look at two different scenarios. The first is where we have a ramp that comes up that raises the elevation by half a foot from the original datum to this. And so we know that when we do that, then the downstream behavior, this original Z1 at the upstream location is what? Yeah, I heard someone whisper it. And so at this location, it's going to be, initially it's going to be 0.5, right? This allows my brain actually catch up with my hand. And so what's going to happen? Where are we going to be on this specific energy diagram? Well, we know that we go up by 0.5. So we know that the change in energy is going to be the upstream energy, which we know, minus 0.5, right? Just subtract 0.5 off the left-hand side, and we end up with 0.2. So physically on this chart, that means going from this point here, going 0.5 meters to the left, and then we have this new point, this line. So this will be the downstream energy once we've climbed up to this point. Ignore this bump for now. So once we're at this point here, and we look at what the energy is at point 2, bracket, bracket, then we know that the depth of flow, and surprisingly, well, perhaps not surprisingly, we're constricting it, so it has to speed up. And if we speed up, actually the level drops slightly. And so the upstream level at this point, y2, is going to be a little bit lower. It's going to be 1.75 feet deep. Deep from this point, right? So it's going to be 0.5 plus 1.75, which I guess is 2.25-ish. So it's slightly smaller. And so that's fine. So that allows us to be able to say, and so this free surface here on the top is for that case where we have the ramp, as it says right here. And so what else can we do? Well, the other thing we could do is we could put a big boulder in the river. And the big boulder is the fact that we have this hump. It's not a boulder, it has to be all the way across the river because we're looking all the way across the flow. And what happens if we put a bump on top of this ramp, which raises the height here to 0.89 feet above this datum? And it's not chosen arbitrarily for this. So we do exactly the same now. So instead of being 0.5, this is 0.89. And I can't draw it. Oh, 8's are the tough ones. I wish it wasn't an 8, and 9's almost as tough. So that's 0.89. And so we do exactly the same. So we come from this point and we go 0.89 to the right. And so it starts off here. It turns out that 0.89 gets you exactly to this nose. That's why it's chosen. And so what it means is that as you go from this upstream location, which is subcritical, we're on the subcritical, we're at a Froude number which is less than 1. We go to this point here. At this exact point here, it's exactly on this nose here, so it's supercritical. So now the water has a dilemma, right? It's sitting right on this nose. It's the same as doing this calculation whereby if you have a bowl and you have a ball bearing rolling around the bowl, you know that when you let that ball bearing run, like in a roulette wheel, it just sits in the bottom of the bowl and it can't go anywhere. It's the lowest potential energy it has. Everywhere it tries to go to be able to reduce that potential energy by going down, it can't get there because it has to go through the bowl to get there. If you take the bowl and you turn it upside down and you put it on top of there, and then it can reduce its potential energy by running off in any particular way around it. And so you can think about this nose kind of like that. So instead of being like this, it's like this. So it's sitting on the top of this nose if you just draw the diagram over. And now it can go, if it's going to get to this now deeper condition, it can go either in this direction upwards, or it can also physically get to this direction downwards. Before, when we went just up the ramp, we could go from 1 to 2, and we're stuck with this new depth, which was slightly different, but it didn't allow us to go through this point here and get to this other point here. But now what we've done is we've gone down this curve, we've got to the minimum energy, the Froude number equal to 1, and now as we go downstream and the depth changes, then we have the option now to physically get to this new point, and this new point, of course, would be on the same trajectory as the ramp was before, so we could end up either at this point here or at this point here. And it could be either, actually. I'm not sure how to choose between them. But this is the way that it would potentially choose to get to this supercritical regime, where now it's flowing very thin and quite fast. And so what the profile of the river would look like is come along here, allows it to go down to the Froude number here, which is 1, and then as it goes around here, it keeps on going down to this new reorganized level, which is this level here. And you know, if we drew this bump in the same place, it would kind of be aligned like this. So that's kind of the interesting behaviors that you get for these free surface flows. And again, it comes back to this observation that because we're not fixing this upper level like we do in a pipe, if you fill a section of a pipe, it has to completely fill that section of the pipe, and you change the pressure upstream and downstream or the gradient, it still fills the section of the pipe, and so the cross-sectional flow doesn't change. Here we actually have the freedom to be able to do that because we can either flow slowly and deep or quickly and shallow as we go downstream. And so that's the mechanism basically for hydraulic jumps. And so I'm not being able to move between these very well, There is a video in here. Let's watch it so I can stop talking just because it's. I'm happy to talk, of course, you know that. Did anyone get text, by the way? By our colleagues who are not here? The hydraulic jump. Is it running? It seems severely challenged today. Oh yeah, so not so challenged. Let's see if it does it. Is anything being said? Can't hear it. Thank you.
Before we start the lab exercise, we must first. This lab exercise is to explore the hydraulic jump phenomenon. The objective is to learn what the hydraulic jump is and be able to properly create and measure a jump. Before we start the lab exercise, we must first learn a few definitions. The first important definition is critical depth. The critical depth represents the depth representing the minimum energy. Critical depth is dependent only on the flow rate and the geometry of the channel, as shown in the
That's for
equation.
Froude number 1, right?
Using
That's
the critical
nose, the
depth,
tip of the
we can
nose.
classify the flow. The first classification is supercritical flow. The flow regime is supercritical when the flow depth is less than the critical depth for the given flow rate and channel
It does get more
geometry.
exciting by the way.
Supercritical flow is generally associated with steeper slopes and mostly occurs in man-made channels. Some examples of supercritical flow are flow in street gutters, flow down a spillway, or flow in steep concrete channels. The second classification of flow is subcritical flow. The flow regime is subcritical when the flow depth is greater than the critical depth for the given flow rate and channel, causing the depth of water to be defined. We can define the hydraulic jump. A hydraulic jump occurs when a zone of supercritical flow discharges into a zone of subcritical flow, causing the depth of water to cross critical depth. The transition between the two flow regimes is associated with a large amount of energy dissipation. Common locations of hydraulic jumps are spillways, where the spillway discharges into the natural channel.
So he mentioned that one of the reasons for this occurs is because of a large amount of dissipation of energy. And so it turns out that the things we talked about so far actually aren't good enough to deal with hydraulic jumps. Hydraulic jumps are actually rapidly varying flows. We're talking about gradually varying flows. And so if there's a huge amount of energy dissipation here, then you can't assume that the upstream energy and the downstream energy are the same. And therefore we need something slightly different to deal with it. But let's not worry about it.
It is of interest in engineering to know the ratio of flow depth across the hydraulic jump. This ratio can be computed by momentum conservation across the jump, as shown in the equation. We are now ready to go into the laboratory and create hydraulic jumps using a hydraulic flume. Protective clothing is a good idea, but not required for this exercise.
Shall we skip through this a little bit, ladies and gents?
To change
Water, we have water.
with a defined time
So
interval.
measuring a flow rate, a volume and the time, so time into a bucket, that's it. Measure flow rates.
Given a channel width of
So it's just a
76
plexiglass
millimeters.
channel. You can see it flows into the left-hand
To
side.
help us create the hydraulic jump, we can mark critical depth on the side of the flume and use it as a reference point for supercritical and subcritical flow.
And so the interesting thing in this is that this will happen merely without putting this ramp in the system at all. And so, let's see this.
We need to force supercritical flow upstream. This is done by inserting a sluice gate and setting it to the desired level.
Where is this, by the way? Any idea? What's the accent? Yeah, I think it's Canadian. Yeah. That's right, eh? Oh, it's always in the basement because water's heavy. Well, you know the tragedy in Latvia, right? Someone put a garden on top of a supermarket. Gardens have water on them, and it failed, killed 30 people, right? Just last week, wasn't it? I seem to remember. So yeah, so this is exactly what we had before. On the left-hand side, upstream of the sluice, you see it's subcritical. It comes out of the bottom of the sluice. It's supercritical, and then for no apparent reason, it just transitions as a hydraulic jump as occurs.
The sluice gate will back water up behind it. Check to make sure the water level doesn't get too high and start
so you get
leaking.
the idea. So let's switch it off. And so it's not really different from what we looked at here. If you look at it closer, and that's what accent is that? Italian, I think, right? Or Spanish? I'm not sure. And so this is basically the idea as it goes from left to right and it changes elevation. So it's really a manifestation, if you like, of this specific energy diagram. But I made the point before that it's not quite good enough to be able to do with this one-dimensional flow regime that we have. And the problem is that a huge amount of energy is getting dissipated in here, and because of that we can't assume that the upstream and the downstream energy amounts are the same. And so if we want to look at being able to understand that very straightforwardly, well, hopefully we understand this. A lot of other stuff, don't need to worry about that. But if we look at so-called rapidly varying flows, so that what we've looked at so far, everything we looked at with this energy, specific energy versus depth diagrams for these gradually varying flows, and those apply. And so that's fair game on the test. The stuff beyond that, let's take that off the test. We won't do with that. So for these rapidly varying flows, the other thing that we need to do or note is that as you go from the upstream to the downstream, so this is supercritical flow, subcritical flow, that this energy grade line, instead of being continuous and having some slope to it, all of a sudden it takes a jump and it goes from some magnitude upstream to a different magnitude downstream. And so this idea of being able to go to this diagram as we had done here, way back here, remember what we did was we got the upstream flow and we went across here to this diagram until we hit this upper point, and then we could go directly down from there, and we knew that the energy on the same curve was the same energy upstream and downstream, so we could get the depths. If we don't have the same energy upstream and downstream, then we can't do that, obviously, so we need some other solution to deal with it. And so it's been observed that to deal with that, we have to just account for something else. And what we account for is that instead of just solving for energy, which is the Bernoulli equation with the loss in it, we solve for momentum. And so this is just our momentum equation. Upstream, so you isolate a free body diagram, upstream force, downstream force, and the rate of change of momentum. Momentum is mass times velocity. So it's mass flow rate. So this is mass flow rate. So remember, this is m dot, and this is velocity, these two terms. And we equate that to the forces on the system. Don't have to worry about it. But what we get out of it is, if we use the momentum equation, we end up with a new term, which is a bit like the energy term, right? Remember, we had energy as equal to two parameters, one of which represented the pressure term, and one of which represented the v squared over 2g term. Well, in the momentum equation, we also get two factors, which represent the pressure term and the velocity squared term. But they're written in terms of the flow rate per unit width. And so for a hydraulic jump, what we have to do is we have to use the momentum equation. We can use the energy equation, but clearly we can use continuity as well, right? Volumetric flow rate upstream has to equal the volumetric flow rate downstream if you're not accumulating volume somewhere in between those. And so to do that, the best pictorial view of this is this. So we can look at the hydraulic jump, upstream supercritical, downstream subcritical. The energy grade line has this discontinuity in it, this jump in it, so we can't actually use it. And we actually don't really know exactly what it looks like. But what we could do is we could plot these relationships for the depth of flow with energy, just by changing, for a given flow rate, we change the depth and we get this single line here. We can also do that for this, right? We can plot the momentum as a function of flow rate. The units of momentum on this diagram have to be depth on the one axis and length squared on the horizontal axis. So in other words, we know the flow rate, we take the depth equal to 0, and we get and change the value up to whatever we want, and we get a curve. And then what we do know is that if we know that the upstream depth is this, and we can conserve momentum, then we know that momentum downstream has to be this amount here. And so immediately from that, we know what the depth would be at the downstream location, just by going across there. And so all we've done here is we've conserved momentum in this particular case, and it's just that we don't satisfy this requirement that energy upstream is equal to energy downstream. If we wanted to look on the energy diagram, then what we'd have to do is we still know that the upstream depth is this, so we can still go across to this point here. Actually now we know that the downstream depth is this, which we've calculated, and so we could go straight across here, and the energy in the system would be this point. And so we see immediately from this that these two amounts of energy, downstream, and upstream, aren't the same amount. And the difference between those is this jump as we go across the upstream to downstream. So I think it's really all pointing to this desire that we have, is to be able to figure out, for the more complicated cases that we have, where we don't have simple channel flow, uniform flow, we can calculate what the upstream and downstream magnitudes should be. We know that all those regimes should plot on this curve, and it just matters how we define the behavior upstream or downstream as to how we calculate what the depths are. And so I know some of you might be scribbling that down. So it matters in the first two cases when we deal with gradually varying flows, we assume basically that E1 equals E2. And painfully I'm going to have to write it out again below. But for where we have these rapidly varying flows, we just assume that E1 is not equal, you can probably write it faster than I can do this, is not equal to E2. But that, can you tell me what is true? Whoops, I feel like Rain Man. But the momentum upstream and downstream is the same. And that's just what we've done. So I'm not sure what to say in summary. I mean, I think the summary is really on this one slide. And that is that the easiest cases that we can deal with, and certainly a fair game, is that upstream and downstream elevation, depths of flow are the same, in which case we can use these the Chezy or Manning formulae to get either velocities in the channel or volumetric flow rates in the channel, which is kind of the same as pipe flow calculations. If we have conditions where the channel is steeper, that we go into these gradually varying flows, then the way that we solve for those are to do this specific energy versus depth diagram. And we've talked about the logic of what that means in terms of supercritical and subcritical flows in different parts of it, and the minimum values. And the interesting thing is that those are all calibrated based on this one number, which is the Froude number. And so these different regimes mean, if you like, if you go back to this hopefully you've got that down. If you go back to this case where we talked about this behavior here, so if you plot, for instance, energy versus depth, so that's supposed to be the 1 equals y equals E line. And so if you plot this curve here, then this value here is critical flow, Froude number of 1. This is supercritical, and this is subcritical. And the interesting thing is that this is based on is that when you're flowing supercritically, this is the case where you drop the pebble in, and the ripples from the pebble never get upstream. So it can't send any information upstream so it knows what it's doing. That's why it can reorganize itself into any particular way it wants, is because it has no way of being able to tell the upstream what it's attempting to do, which is one way of looking at it. And so it's interesting that there's this kind of commonality between this nose here is a Froude number of 1. We know what the coordinates of this point are in terms of 2/3 or 3/2 times the critical depth. And we know that ultimately at very high flow depths, this y equals E line is what the flow rate's asymptote.